Nanoscience offers one of the most exciting new areas of discovery for scientists. Today, nanotechnology is creating new materials, medicines, sensors, and devices at the molecular level. At REVELANT, we use nanophysics to engineer our tools to perform at the nanoscale. Here we see the scale of nano. In the lower left, one water molecule is about 1/10 of 1 nanometer, and in the upper right side, we see one human hair, which is about 80,000 nanometers. Now, imagine the diameter of a tennis ball as 1 nanometer, and the diameter of the Earth as 1 meter. That order of magnitude is powerful. At REVELANT, we harness the power of nanophysics to improve the chemistry of fluids. Specifically, our focus is oil and water. The world runs on these fluids, and during their transport, changes in temperature and pressure create fluidity and stability problems. Traditionally, the problems of oil viscosity, paraffin crystallization and buildup, asphaltane aggregation and flocculation, and scale depositions in water have been addressed remedially with chemical, mechanical, and thermal inputs. At REVELANT, we reduce these recurring problems with physics. We do it by improving nanofluidity, which maintains fluid stability and prevents particle dispersion beyond the nanoscale.
That's where the ENERCAT tools come in. At REVELANT, we make use of the properties of material composites. Basically with material composites, they have lattice vibrations. The ambient energy or the ambient conditions surrounding the ENERCAT tool serves as the hammer to drive the oscillations and vibrations through this material. The material is such that some vibrations and frequencies will survive moving through the material and others will not. This is constructive and destructive interference. The frequencies that survive the tool serve to influence the fluids at the nanoscale. This is what REVELANT defines as nanofluidity. At the nanoscale, we have the opportunity to use quantum effects as well as classical mechanics in order to drive molecules in the direction that we choose. The key, again, is to make sure that we're making stable dispersions. In order to do that, we're going to drive vibrations within the molecules such that we can move from a local energy minimum to a second. The key is that when we're talking about large floppy molecules, those energy landscapes are very rugged, which means there's multiple energy minima that have approximately the same amount of energy, but that may have very different physical properties. And we want to move from one energy minimum that has less desirable physical properties to a second that has more desirable physical properties. As an example, we can consider the scale problem. The scale problem really develops out of calcium carbonate depositing as calcite. Calcite is such that it interacts strongly with things like metal pipes. Calcium carbonate, though, does have other crystal polymorphs, for example, aragonite and vaterite. The key is that aragonite has very useful properties, including the fact that it does not want to interact with metal oxides, which means that we can maintain calcium carbonate in solution as aragonite rather than calcite. What we do is use the tool in order to seed aragonite crystals in a dominant way over calcite crystals, thereby improving the molecular solubility of calcium carbonate in solution.
This is just one example of the power of physics in fluids. The ability to measure, tune, and focus nanophysics in oil delivers a safer, less expensive, and green approach to optimize production and enhance recovery. In the near future, Big Oil will use it to unlock stranded oil, increase booked reserves, and extend the life of reservoirs and pipelines. The future of nanofluidity in water will change things. Industrial water problems will disappear, agriculture will need less fertilizers, turning water into steam will require less energy, and imagine desalinization of water with nanotechnology. We invite you to connect with us and explore how we can pioneer the nanofluidity frontier together.